This video is going to discuss general and specific antiderivatives. If you have not watched the video on Introduction to Antiderivatives that I have posted on my channel, please be sure to do so before watching this video. Okay, so in this video we're going to essentially find antiderivatives, and then there's going to be constants that we have to add or subtract. So in the previous video on in that introductory video, we discussed that if we have a function, okay, and we want to find its antiderivative, right, then we need to undo that differentiation process. So we need to think, okay, well, derivative, so sine is the derivative of cosine, okay, and normally if I differentiated cosine, I would end up with a negative sine x, which is not present here. And then if I differentiate this function, I would have normally a multiplication by pi, right? But there's no multiplication by pi present. So to undo that, I need to do division. So the antiderivative here is -1 by pi cosine pi x. Now, technically, when we do the antiderivative, we get a solution family, meaning that we don't get just one solution, we get infinitely many solutions, because in reality, there's always a constant. There could be a constant. We don't know. It could be there, it might not be there. But remember that when we differentiate, so again, if I now take the derivative of all of this, I can do the derivative of this first part, so -1 by pi cosine pi x. That's going to give me the sine pi x. But when there may be a constant there, I don't know, because when I differentiate a constant disappears. So when I anti-differentiate, I always need to make sure to include a constant. And that inclusion of a constant, in a general sense, we're going to call an antiderivative. If we have a particular value, okay, if we have a particular value for c, then it's a specific antiderivative. Okay, now that specific value so that constant value could be 0, could be 1, could be 42.5. I don't know. To find out that value, we'll see in a couple examples, but we can actually apply some sort of initial condition, okay, if it's given. If it's not, stick with the general antiderivative and you'll be fine. Okay, so let's go through some examples here. So we want to find each antiderivative, and in some cases we're going to find the specific antiderivative in instances where we're given a condition. If we're not, we're just going to leave it as the general antiderivative. Okay, so looking at little g of t here. Okay, this is going to take some practice, but this is reminiscent, so I'm just thinking, this looks like 1 over t. Okay, and 1 over t, that was the derivative of natural log. Okay, so what I'm thinking is that if I look at the antiderivative of little g, so I'm going to label that as capital G of t, this is equal to the natural log of the absolute value of t plus 1. And I need to make sure to have absolute values there. That's absolute value. And we can differentiate this, and so again, if I differentiate this, this would be g of t is equal to 1 over t plus 1 times the derivative of the input, which is just 1. Okay, so I think my formula for the antiderivative capital G of t holds, and then just make sure to include a constant if we're not given any initial conditions. Okay, so that one, we found the antiderivative for the first one. For the second one, okay, f of w, okay, great. So there's a bunch of constants in here. I don't really care because w is my only variable, so I'm only paying attention to that. Everything else I think is a constant. Pi is a constant, 3.14. So in finding the antiderivative of little f with respect to w, I need to think, okay, well, there's going to be a chain rule going on here, okay? Or if we remember our formulas that we went through in the introduction video, we would say that this is going to be, the antiderivative is going to be negative pi over 4 cosine of pi w over 4. Okay, maybe perhaps take a little bit of time and verify this on your own, but again, you could double check this by performing differentiation. Okay, so, and then I always want to remember a constant on there if there's no initial condition given to us, which there isn't. Okay, and I'm going to clean this up just a little bit. I'm going to write this as negative 4 cosine pi by 4 w. Okay, that's fine, plus c. So that would be my general antiderivative for this one. Okay. Again, you can check it by performing differentiation. Okay. For the next one, h of p, notice that we're given, this is the form of an initial condition. So this, in this example, we're going to find a specific antiderivative. Okay. Now, h of p, okay, this is a derivative. Okay. If I want to find the antiderivative, it's going to be e to the same power divided by the derivative of the power, or divided by 1/2. Okay, and so I think this is just going to be, and I'm going to include the constant for now. We'll find its value in just a minute. So this is 2e to the p over 2 plus c. I'm going to check this one super quick just to make sure. So if I compute h prime, this is going to be 2e to the p over 2 times 1/2 plus c. But the c derivative constant goes away, so that's gone. And this is just, let's see, 2 and 1/2 cancels, so this is e to the p over 2. If you're ever unsure with your antiderivative, differentiate it, and you should get the same result back as what you started with. Okay, so I found my general antiderivative. Now I want to find my specific antiderivative, so I want to apply this initial condition. What this is telling me is that p is 0, or p is 0 when, let me rephrase that, when p is 0, h, capital H, is 1. So I get the equation 1, h of p, is equal to 2e to the 0 over 2 plus c. So this would be e to the 0, anything to the 0 power is 1. So this is the same as, I'm just going to make a comma here, 1 is equal to 2 plus c, or c is equal to minus 1. So my specific antiderivative, capital H of p, is 2e to the p over 2 minus 1. Okay, applying the initial condition is just algebra, and then always make sure to rewrite your specific antiderivative with that value of c in there. Okay, now the last one, we are going to do this piece by piece. Okay, so we're given a function m in terms of y, and we are given this as the function, and then we're given an initial condition. Okay, so if I find the antiderivative, capital M of y, okay, the antiderivative 4, when I antidifferentiate it, is going to be 4y. If I look at minus y, the antiderivative, okay, by the power rule, I'd have to increase the exponent by 1 and divide by the exponent. And then same thing with this last term. Since it's a polynomial, I would add 1 to the power, and then divide the coefficient by the power. And always remember the constant. So this is 4y minus 1/2 y squared plus 3y cubed plus a constant. Now I use my initial condition, so plug in 1 for y, and then m is 5/2, so it's 5/2 is equal to 4 times 1 minus 1/2 times 1 squared plus 3 times 1 cubed plus c. So this is 5/2 is equal to 4 plus 3 is 7. 7 minus 1/2 is 13 halves plus c. Moving this stuff over, 13 halves minus this should be minus 4 is equal to c. So then my end result here, my specific antiderivative, m of y is equal to 4y minus 1/2 y squared plus 3y cubed minus 4. Okay. And so that's a bit on general and specific antiderivatives.